Yesterday we stopped here, and this is about the Gauss law, actually the most important part for this chapter, and actually very important point for this semester. Actually, you will use this Gauss law from this chapter on, and maybe for 2 or 3 chapters. Chapter 24, 25, you still keep using this Gauss law. So actually, it is very important. So here is about So we'll define what is called a Gaussian surface, which is a closed surface. And within the closed surface, we can check the net charge inside this Gauss surface. Maybe there are some positive charge and negative charge, but you just add all them up. The position of the charge distribution is not really important. The charge distribution is not really important. You only need to care about what is the net charge. You only add them in a scalar sense. So you get the Q enclosed whether it's positive or negative. If it is positive, then the flux will be a positive number. And if it is negative charge, then the net flux will be inward. And actually, the flux can be written as the closed surface integral form like this. So this is what we'll use in the future. So here's a simple example. If we have S1 here, it encloses a positive charge. So although this change is its shape is very strange, but you can consider this flux. You integrate the E dot dA over this surface. It should be a 3D, but actually I can only draw 2D here. So you can calculate the E dot dA, and the Q enclosed is discharge, so it will satisfy this this equation, this Gauss law. Actually, if I just draw it like this, so it encloses the same amount of charge. So the integration over this surface and this surface will actually be the same. So for S2, it encloses a negative charge. So if you calculate this one, it will have a negative value because all the E field are flowing inside. So you have a negative charge, so it will satisfy this one. So we can see that a phi2 should be a negative number. A phi1 should be a positive number. And S3, it encloses nothing. So even though some of the E field flowing inside and some of the E field flowing outside, but you expect this phi3 would be perfectly zero. And for the S4, which is the largest Gaussian surface, so it encloses this positive charge and this negative charge. Of course, if we assume the charge amount are the same with opposite sign, so the net charge enclosed by S4 should be 0. And in this case, phi4 should also be 0. So this is the Gauss law, and yeah. So here we talk about Gauss law and Coulomb's law. Actually, they are compatible with each other. So here we assume we have a positive charge, or actually it can be a negative charge, but here is shown a positive charge. So we assume a Gaussian surface to be a sphere, and the charge is at the center of the sphere. So we can apply the Gauss law to it. And actually, we have epsilon naught multiplied by this closed surface integral. And actually, all the distance between the surface to the center should be all the way the same. And actually, E should be have the same value, should have the same direction as the dA, because dA is perpendicular to the surface. So actually, E vector and dA should point to the same direction, which means that E dot dA is actually EDA cosine 0 degree. Cosine 0 degree is 1, so it will be like this. And then this is Q in charge is small q, or maybe I can write it as Q enclosed. So here, E is uniform over S, and then we have, because E is uniform, because we'll assume the center to the surface would be a constant distance. So E is a constant, so that I can just put it out, and then the surface area of the sphere would be 4 pi r squared. So I can just put everything in, and then I can just rearrange the term, put epsilon naught 4 pi r squared to the right hand side, so that E will be nothing but this. Actually, this is what we have learned in chapter 22, the last chapter, and it comes from the electrostatic force or the Coulomb's force. So actually we define E equals to F over Q0. Then we can come up with this expression. And actually I can also use Gauss law to derive this one, which means that the Gauss law and the Coulomb's law are compatible with each other. So far, any questions? So next, we have a sample problem. So in cross-section, a plastic spherical shell with uniform charge Q, radius R, a particle with charge Q, small q is at the center. So this is at the center. We have this one, should be a sphere. But if I draw it as a sphere, then you cannot see what is inside. So it's just a cross-section shown here. So what is the electric field, magnetic magnitude and direction at point P1 at radial distance R1 equals to 6 centimeters. So here, so here we can consider a Gaussian surface to be here, Gaussian surface to be here, so that we can apply the Gauss law for this Gaussian surface. So epsilon naught equals to this one, Q enclosed. Q enclosed is nothing but small q, because a capital Q is outside. Capital Q is distributed uniformly on the sphere. So if I draw a Gaussian surface here, which means that the Q enclosed is nothing but small q. So in this case, we'll assume all the charge is symmetric. So E should be uniform, and then E should be pointing parallel to the radial axis. R is called the radial axis. Radial axis, parallel to the radial axis, which means that EDA is nothing but E dot dA should be equal to EDA. So in this case, we can write epsilon naught E dA equals to Q. So similarly, we have a E 4 pi R square, R1 square. This one is R1, and then R1 square equals to Q. So at point P1, E should be 4 pi R 4 pi epsilon naught. 4 pi epsilon naught, and then Q over R1 square. Q over R1 square. So we can just plug in the value 8.99 times 10 to the 9th power, and then times Q is 5e, which is 5 times 1.6 times 10 to minus 19. And then R1 is 6 centimeter, which is 0.06 quantity squared. So this one will be 2 times 10 to the minus 6 Newton per Coulomb, or you can write it as a 2 mu n per Coulomb, or so actually calculating the E field, for the direction it should be pointing outward. So actually, when we calculate the E field at point P1, so it's just like we can't really see this sphere. We can't really see this sphere. Actually, without this sphere, the E field is actually the same at point P1. So it's just like this one. This is the E. So any questions? Okay. So next one, we will try to calculate. Actually, the question is the same, but we actually want to calculate the E field at point P2. So this point. So here we will consider a Gaussian surface to be here. So actually, we use the Gaussian surface like this, Gauss law like this. Q enclosed for part B. So for this one, Q enclosed includes both capital Q and small q. Small q and capital Q are both inside this Gaussian surface. So which is nothing but minus 16e plus 5e, which is minus 11e. So for this side, we can do the similar things. So it's just like EE 4 pi. This is R2 square. So this is R2. So equals to minus 11e. So in this case, or here maybe you can just keep it like capital Q plus small q, and then you can get the closed form like E equals to 1 over 4 pi epsilon naught R2 square Q plus Q. So actually this sample problem is related to the shell theorem, if you still remember. Shell theory in chapter 21. So maybe actually this is about the shell theory. Maybe I finished the solution first. So here 4 pi epsilon naught is 8.99 times 10 to the 9th power, and then Q plus capital Q plus small q is minus 11e, so it is minus 11 times 1.6 times 10 to the minus 19. So over R2 is 11 centimeter, which is 0.12 quantity squared. So E should be minus 1.1 times 10 to the minus 6 Newton per Coulomb. Or you may write it as minus 1.1 mu N per Coulomb. And then of course this value is negative, which means that the E should be inward. Yeah, you may have a question why we don't have a negative value here. Actually, you can just assume E to be pointing outward. So E and dA would point to the same direction rather than opposite direction. And then finally, we come up with a negative answer, which means that if it is a positive answer, which means that E field should point to the outside. And here, if we have a negative answer, which means that the E field point to the opposite direction, which means it should be inward. Okay, so far any questions? So if no question, I come back a bit. So this is about the shell theory in chapter 21. Chapter 21, you can check it back. So this is chapter shell theory 1. So at that time we mentioned that if suppose inside a sphere, then this one will generate no E field inside the shell. Generate no E field inside the shell, because here we can just simply use Gauss law. Suppose we have a sphere, and then if you just neglect this small q, suppose we have a sphere. With charge q, and then we may consider we have a Gaussian surface, maybe here or here. Then it encloses nothing. Q enclosed should be 0. If I just draw a Gaussian surface smaller than the sphere, then we know that phi, then according to the Gauss law, we know that phi should be all the way 0. And if this Gaussian surface and the sphere share the same center, so it should be symmetric. Which means that suppose that this one sum up to be 0, and it means that for all the points on this Gauss surface, the E should always be 0. So that it sum up to be 0. It shouldn't be like some is positive, some is negative, and they cancel out. As long as we draw the sphere which share the same center. So this is the shell theory 1. We can check it back later. This is the shell theory number 2. So here, for shell theory number 2, it means that if we have a sphere, and then the charges distribute uniformly, and then suppose we have a Gaussian surface outside. So it's just like the charge. Suppose the charge is distributed on this Q, is distributed on the sphere uniformly. So it's just like we have Q, or just all distributed at the center. So in this case, if I draw a Gaussian surface, I'll suppose this these two graphs are independent. They are not at the same space. So this one is equivalent to that one, because if I draw the Gaussian surface here, the Q enclosed is small q. If I draw Gaussian surface here, the Q enclosed is also a small q. So which means that phi, this phi 1 should be equals to phi 2. Phi 1 should be equals to phi 2 for this one. And in that case, as the Q is distributed uniformly, so we'll assume E is also uniform. So in this case, phi 1 and phi 2 are equal, which means that E on this Gaussian surface should be the same as the E on this Gaussian surface. So this is the shell theory number 2 in chapter 21. So far, any questions? Okay, so we have a next sample problem. So we have seen it yesterday, and actually we have already calculated phi left, phi right, and phi top at that time. So it is obvious that phi front and phi back, it should be back. Phi back should be front. Front is this side. This is front. This is front, and that one should be back. That one should be back. If you have ever played the magic cube, you know, top down, left right, front back. So as long as the E only points to the x direction and right direction, and for front and back, the dA for front should point to the c direction, and the front and for the back, negative c direction. So for the dA. So you can simply imagine that dA dot E for front and back should be 0, because there are no k. This should be k dA. This should be minus k hat dA. So k hat dot with I hat or j hat should be 0. So you can imagine phi front and phi back should be 0 also. So the remaining term is the front bottom, phi bottom, I suppose. Yeah. So the question here is, what is the net charge? What is the net charge enclosed by the Gaussian cube? So actually we still need to calculate the phi bottom. Maybe this one is back, that one is bottom. Bottom is like this. For the dA, it should be point to the negative y-axis, which is minus j hat dA. So phi bottom should be E dot dA bottom. So E should be 3x I hat plus 4j, and then dA should be this one. So it should be dot minus j hat dA. So I dot j hat should be 0, j dot j hat should be 1. So minus 4. So we have minus 4 dA. So it should be minus 4 times 4, which is minus 16 nm squared over c. So for this, suppose the Gaussian surface is this cube. So the total phi should be, you add up all the stuff. So it should be minus 12 plus 36 plus 16 plus 20. And then this minus 16. So it sums up to be, let me see, 24 nm squared over c. So actually we can just simply use Q enclosed equals epsilon naught phi, because we already calculate the integration. So it turned out to be something like this. So epsilon naught is 8.85 times 10 to the minus 12. And then this is 24. So the answer will be 2.1 times 10 to the minus 10 C. Or you can write it as 210 picocoulomb. Any questions? Yeah, I remember yesterday after the class, someone has asked me, what is a Gaussian surface? Is it really a practical existence? 是不是真实物理上存在的？Actually, it's not. It is just a surface based on imagination. 它只是出现在你的想象里面的。你想象那个Gaussian surface 长那样，它就是那个曲面，So it is a surface which does not really exist. So you can imagine, the Gaussian surface can be a sphere, can be a cube, can be whatever shape like this one. So it's just based on imagination. It doesn't really necessary to be a shell or a solid object. Okay, so we talk about this one. So the charge isolated conductor. So if an excess charge is placed on an isolated conductor, that amount of charge will move entirely to the surface of the conductor. None of the excess charge will be found within the body of the conductor. So this means that if you have a solid conductor, so conductor is a very key term. It's a key term. So in chapter 21, I introduced that conductor which has sufficient amount of free electrons, which means that the electron can be free to move within the conductor. And if it is an isolator or non-conductor, which means that the electrons are not free to move. So usually they will assume, there will be a distribution, or maybe they can uniform distributed even inside the non-conductor. But for conductor, it tells you that suppose there are some excess charge, no matter it is positive or negative charge, then all the charge will go to the surface. Okay. all the charge, maybe if it is a positive charge, all the charge will go to the surface. It will not stay inside. It will not stay inside. It will be the same case if it is a negative charge. Then all the charge will go to the surface for conductor. For conductor. So here it talk about here we have a metal. We have a metal. Yeah, suppose it is a very large piece of metal, and then it try to calculate the E field generated by this metal with excess charge. So here, suppose we have a very large metal with positive charge, and then we assume the Gaussian surface is a cylinder. Actually goes in the metal. So it's somehow like you can imagine. Suppose this is the surface of the metal, and then this is the Gaussian surface. Suppose you imagine, you just ignore the cap, so you imagine it's a perfect cylinder. So it's somehow like this. So half of it is inside the metal, and then half of it is outside. So it's somehow like this. So you can check, this graph is the cross section, so that you can only see the rectangle here, but actually it's a cylinder. So half of it is outside, half of it is inside. So we can assume that all the E field should point to the outside, because there is no excess charge here. And if there is no excess charge, then you can imagine I can try to draw many different Gaussian surface. As mentioned just now, as long as there are no excess charge inside the metal. So if I just draw a very large or arbitrary Gaussian surface inside the metal, then there are no Q enclosed. So Q enclosed will be 0, and in that case, there should be no E field inside. Because you can just change the shape. Maybe you change it a little bit, and then there are still E. So this part should have no E, and then you can keep doing this stuff, and then you will know that for conductor, the E field should be 0. Okay. So for outside, due to the symmetric, we will suppose all the E fields should point to the right side. For this graph, all the E fields should point to the right side. So for the Gaussian surface, for this one, so dA should point to the right side, and the E point to the right side. So E dot dA would be a positive number. So for this one, we have E times A. But for this side, yellow is not a good, green. So for this side, dA should point to should all the way perpendicular to the E field, which means that for this one, E dot dA will be all the way to be 0, so that this one will contribute no phi. So in this case, here we only have EA. And for that part, because there are no E field inside, so that surface will not contribute the electric flux either. So on the left side, we only have this term, and Q enclosed, we will also assume this is the surface charge density. And then this is the area. So this is the area. And A and A can be cancelled so that we come up with this expression. So it's a constant. It only related to the surface charge density, and also the epsilon naught, which is 8.85 times 10 to the minus 12. So in the last chapter, we have derived this one, and also if we assume this charge is infinitely large, we can have E to be sigma over 2 epsilon naught, because in this case, we'll assume E will be point to the upper, for the upper part, and point to the bottom, point to the lower side for the bottom part. So here we have a sigma over 2 epsilon naught for the upper side, and epsilon naught to epsilon sigma. So we have a factor of 2, because we have half of it on the upper side, half of it on the lower side. But here we assume this is a very large metal, so all the E field would be at the right side. So it only generates the E field on this side. So it's a factor of 2 times larger than this one. Any questions? Okay, so we have another sample problem. So here, So here the figure shows a cross section of a sphere. Of a sphere metal shell of inner radius capital R. So capital R, inner radius, 那个内半径. So a point charge of -5 mu c is located at a distance R over 2. So this is -5 mu c. If the shell is electrically neutral, what are the induced charge on its inner and outer surface? As those charge uniformly distribute, what is the field pattern inside and outside the shell? So actually, it's not really possible to explain why it would be curving like this. Actually, it's based on many calculation. You need to calculate at this point, at that point. But actually, I can just explain this phenomenon in qualitative view. So actually, we have a -5 mu c. We have a -5 mu c. So actually, we can draw a Gaussian surface at the outside. So the Q enclosed will be 5 mu c. So the Q enclosed will be 5 mu c. And in this case, you will imagine all the excess charge on the outer surface will distribute uniformly. And then there are some positive charge like this. This side will be more concentrated, and this one will be less concentrated. And in this case, because actually the shell is electrically neutral, which means that this induced charge, this negative induced charge and the positive induced charge should be the same amount. They add up to be 0. So actually, the overall enclosed charge for this Gaussian surface would also still be Q enclosed will still be minus 5 mu c. And in this case, the E field 5 mu c should be pointing inward. So all the E field should be pointing inside. It's just like there is. It's somehow like for the outside, if I have a neutral cell there, it's just like the charge is at the center. But actually the charge is not at the center. But if field lies at the outside, I cannot know where the charge is. But actually, if field lies, the charge is at the center, and then you can remove this cell. For the outside is that case, but for the inside is a bit different because this is more dense, so that you can imagine this part, the E field is stronger, and for that part the E field is weaker. So the part is weak. So actually, we can say that 5 mu c charge on the inner surface, because the positive charge, actually the free electron for the shell are repelled by this 5 mu c, so that the remaining inner reduced charge should be positive charge, which would be 5 mu c, and all the 5 mu c will go to the outer surface. And uniformly distributed. And actually, we will call this effect the shielding. So this electrically neutral shell is just like a shield， 像一个盾牌那样，它挡住了里面的，它让外面看不到里面的状况。Okay, so let me finish this part first. So here we try to apply the Gauss law for the cylindrical symmetry. So here we have a very long, infinitely long wire. So it is a section of an infinitely long cylindrical plastic rod. Plastic means non-conductor. So with a uniform charge density lambda. So the charge distribution and the field have a cylindrical symmetry. 它是椭圆对称的。So actually, all the E field should point to the radial axis, and this is a positive charge, so pointing outside. And suppose this is infinitely long, which means that you cannot find the end. So all the E should be perpendicular to this one. So you cannot find this one is although it is upper then, but you cannot find this side is longer or shorter because it goes to the infinity. So in this case, to find the field at radius small r, we can assume there is a Gaussian surface like this with the height small h, with the height small h, and the radius r. So we can use the Gauss law, and actually for the upper side and lower side, the E field should be perpendicular to the dA. dA should be pointing to the upper side, the dA should be pointing to the lower side, but the E field point to the radial direction. So they should be perpendicular to each other. So the only contributing part is here. Okay, it's here. Is this part. So we have E phi equals to epsilon naught EA, and the surface area should be 2 pi r. 2 pi r, which is the length of this circle. And then if you just cut it out and then flatten it, so it will be a rectangle. So the width will be 2 pi r and the height will be h. So the surface area will be 2 pi r h, and then the Q enclosed would be the charge between this point, between this point and this point. So we have h multiplied by the linear charge density. So the h and h can be cancelled, and then we arrange the term so that it will be like this. It will be like this. Yeah. Okay, so let's have a 10 minutes break.